Hello, welcome. Today I'm going to talk about series and parallel circuits. This video is meant to directly follow my two discussions on Kirchhoff's current and voltage laws, and then directly after this I think I'm going to start introducing circuit elements. I think this is the last necessary exercise in generality before we step into those more specific concepts. So let me get started. This is EE 101, episode 6, series and parallel circuits. So to begin, like the last few videos, let me start by drawing this symbol here, just to remind you what I'm talking about. This is a general circuit element. Now let me box that out. Okay, so I'm going to jump right into this. I'm going to start with series and then parallel. And you may have heard these words before. In discussions around circuits, people talk about, oh, that's a series circuit, or oh, that's a parallel circuit. Well, in a lot of cases, you can use these two words to identify circuit elements configured in different ways. So when someone says, oh, that's a series circuit, what they mean is they see some combination of circuit elements configured in something that we call a series configuration, and that's analogously true for a parallel configuration. You have parallel circuit elements that comprise a parallel circuit. So let me try and draw up a definition. Oh, real quick, every single circuit isn't necessarily either one or the other. So series and parallel capture a very large spectrum of possible circuits, but you can create configurations where any two given elements aren't in either series or parallel. That's totally possible. So these are just two large perspectives that will get you very far, and especially in the beginning here in EE 101. So let me jump right into this with series circuits. I want to draw up a general definition for series that's still easy to understand. So let me draw two circuit elements. Call this the series configuration. So let's say we have an element here and an element here. We'll call this A and we'll call this B. So what do I have to do to get element A and element B in series? Well, there's two rules, basically. The first rule is exactly one node, or rather A and B must be connected at exactly one node. So A and B are connected in this way to create a single node. They must be connected at exactly one of their terminals each. So one terminal of A is connected to this node, and one terminal of B is connected to this node. So element A and B share exactly one node. So let's say this. Elements A and B share exactly one node. Okay, and there's a second rule. Let me draw dots off like this, so there's other things happening in this circuit. The second rule is what makes this super trivial, is that, and maybe we'll label this node X. A and B may not share node X with any other circuit element. Okay, this is probably way more words than are necessary to describe a series configuration. It really is as simple as it looks. It's just two circuit elements cascaded. They're going end to end. One leads into the other. But if just to tie up any potential loose ends here, this is the strictest, while still remaining general rule you can concoct here. So all it means is that A and B are only connected together in one place on one side, and it doesn't matter which side, as long as only one side of A and one side of B are connected together at this node, and no other circuit elements hang off this node. So if I was to draw another element here, C, or infinitely many other elements that can sit in this universe here, none of them at any point are allowed to connect to node X. Okay, so if element C connected to node X here, A and B would no longer be in series as I've drawn them here. And at the same time, if you were to connect A and B simultaneously by these open ends here, while node X still exists, then they would no longer be in series. So you just have to satisfy these two conditions, and there you go. That's a series circuit. Now, one thing to keep in mind here is that because they're connected in series, and I want you to think back to my video on KCL so that you start drawing parallels and connections here, well, I think what's probably very clear to most of you is that because they're in series, these two elements have to share current, right? So the current through these elements then, IA and IB, are equal. And so this is probably the idea that you're going to apply practically in your circuit analysis. And I just wanted to be careful here, because you don't want to define the series configuration as the currents are equal. Because in your circuit, you can have equal currents in all kinds of different locations, but that doesn't mean elements are in series, right? It's elements being in a series configuration gives you the consequence of the currents through those elements are equal. And maybe to put it just a little bit more clearly, it's not just that the currents are equal. It's literally the same current flowing through both elements. If you recall, this series configuration here is part of a larger circuit, a larger loop, and so this must be the same current. It continues to flow throughout. Now, let me talk about the parallel configuration. So, let's do the same thing. I guess I'll use different letters just so we don't confuse definitions here. So let's draw an element like this. And we can see that. Oh, let's scoot this up. There we go. Let's draw an element like this, and another element here like this, and we'll call them D and E. So now the rules for a parallel configuration are as follows. Well, first, let me just start by connecting them in parallel. So I'll connect these elements like this. And now let me write the rule here. Elements D and E share both nodes. And that's really all there is to it. It's actually simpler than the series configuration. So, and in fact, let me draw this way. So now, in this configuration, these terminals on both sides of D and on both sides of E are shared, meaning one side of D connects to one side of E, and at the same time, the other side of D connects to the other side of E. So if I label this node Y, and this node Z, D and E share exactly both of their possible nodes. And so this is assuming that we're working with two terminal circuit elements here, right? So D and E just have two terminals each, and they share exactly both possible nodes. So they share node Y, and they share node Z. And so I say this configuration is actually simpler than the series configuration because there's only one rule versus the two rules for the series configuration. And interestingly, there's actually nothing you can do to this circuit other than break these connections. There's no element you can add in any configuration that will cause D and E to no longer be in parallel. Because think about it, there's nothing you can do. All you can do is add another parallel element. But with only two nodes to work here, with exactly one possible point given your two nodes to insert another element, there's nothing you can do. So let's say I had an element here. We'll call it F. And it goes off into the ether somewhere, but is connected. If it's hanging off node Y, and then its other end goes off into the ether, it doesn't matter. D and E are still in parallel. They still share exactly both of their nodes. And now, if I was to add an element here, and what letter comes after F? G. Well, all I've done now is add another element in parallel with D and E. So now all three, D, E, and G, are in parallel simultaneously, but we haven't caused D and E to not be in parallel. And so there's nothing you can do. So as long as this one rule is satisfied, you have a parallel circuit. So in many cases, this is almost easier to identify than the series circuit. And so just like the series configuration had the KCL related consequence, parallel circuits have a KVL related consequence. So something that you'll see by virtue of the fact that we have ideal conductors connecting these elements is that the voltage, let's say the voltage across element D, VD, what you'll see is that the voltage across any element in parallel with another element must be the same across each of those elements. So VD equals VE equals VG. Or sometimes you might see people represent this voltage as VYZ, describing it based upon the nodes that it appears across. So VD, the plus and minus terminals of this element, also correspond to node Y and node X. So this is really the same voltage, and this is common to see that represented that way. And so the just like in the series configuration relative to KCL, it's not that if you just see two equal voltages in a circuit, those elements are in parallel. No, it's that a consequence of elements existing in a parallel configuration is that their voltages are identical. And this is a super powerful tool, just like I talked about here. Being able to apply this knowledge in your circuit analysis, that series elements have equal currents, this is absolutely necessary to be able to solve even the most basic circuits. And the same is true for understanding this relationship with KVL for the parallel configuration. You must recognize that anytime elements are in parallel, they share the same voltage. And so with that in mind, I hope this was as helpful and as brief as possible. Let me know if you have any questions or suggestions for future videos, or if there's any way I can improve the style or content of these little lessons, then please let me know. And like I said in the beginning, I think the next video will be an introduction to some circuit elements. So you can look forward to that. Thanks, and have a great day.